Hello, everyone. Welcome to my talk. This talk is about the role of speech normalization in perceptual learning. To start with, we know that listeners make perceptual adjustments to adapt to talker-specific phonetic distributions. They also generalize these perceptual adjustments that are made across speakers. So in this example, when the listener heard an atypical S from the speaker saying street, he could adjust the mental representation of the phonetic distribution of SH, and further, he could apply the adjusted distribution to the perception of a different speaker's SH. However, we also know that phonetic categorization is not only informed by the phonetic distribution of the target phonemes. Listeners also draw on contextual cues from the talker's speech to make linguistic interpretations, and this process is called speech normalization. And it may apply to the perception of different phonemic contrasts. So in our previous example, the contrast of SH is realized by spectrum cues, and S usually has a higher spectrum energy frequency than H. However, the relative height of spectrum energy frequency is also dependent on the adjacent spectrum cues, such as the formant of this vowel. With everything being equal, if we raise the vowel formants of that syllable, then the sibilants will be perceived to have relatively lower spectrum frequency in relative to the vowel. And listeners are more likely to hear an ash in the latter case. And speech normalization may also apply to temporal cues, such as voice onset time. So in this figure, we can see that T has longer voice onset time than D. But the relative length of voice onset time is also affected by contextual temporal cues, such as the duration of this following vowel. With everything else being equal, if we expand the vowel temporally, then the consonant will sound relatively shorter compared to the vowel, and listeners are more likely to hear D instead of T in the latter case. So synthesizing the two lines of literature, one is perceptual learning and generalization, the other is speech normalization. Our question remains to be, do listeners learn and generalize raw phonetic cues or normalized phonetic cue distributions in perceptual learning? We lay out two hypotheses in response to this question, which I'll explain later. As the test case of this question, we investigate two kinds of phonemic contrasts, each in one experiment. So experiment 1 investigates SH. We ask whether changing the contextual vowel formants of a training speaker would affect the listener's categorization of sibilants in the test speaker's speech. We recruited 45 participants to participate in the experiment online. The experiment consists of a training phase and test phase with a different female speaker in each phase. So in the training phase, listeners did 51 trials of spoken word identification with female A speech. Listeners need to choose what word they hear from two options. For example, they might hear rehearsal and need to choose between rehearsal and reversal. And the stimuli are 17 spoken words containing S, 17 words containing H, and 17 filler words without S or H. The task is simply to provide listeners with exposure to female A's SH and other spectrum cues in general. And in the test phase, listeners need to do another 51 trials of spoken word identification with female B's speech. But the task becomes a little bit harder since listeners need to choose from SH minimal pairs such as sit and shake. Stimuli in the test phase contains 35 critical stimuli and 16 fillers. So the critical stimuli were constructed by splicing 5 steps of SH continuum into 7 lexical frames of SH minimal pair, which are shown here. In other words, listeners will hear 7 repetitions of an SH continuum with each repetition embedded in a different word frame. and all trials are randomized for each participant within the block. And our critical manipulation is here. So participants are randomly assigned to 3 conditions. In the different conditions will have identical stimuli in the test phase and identical SH in the training for the training stimuli. But they will have different contextual vowel formants for the training stimuli. So compared to the normal condition, our participants in the raised condition will hear higher vowel formants with the original formants scaled by 1.2. And participants in the lowered condition will hear lower vowel formants with the same set of vowels scaled by 0.8. And the 2 hypotheses we laid out earlier will make different predictions about our test results. So according to the raw distribution hypothesis, listeners will only learn and generalize the phonetic distribution of the sibilants. And since participants had exposure to the same set of SH in the training phase, we should expect them that they perform similarly across the conditions. By contrast, the normalized distribution hypothesis would predict that listeners keep track of the sibilance distribution in relative to contextual cues. So compared to the normal condition, participants in the raised condition will hear higher vowel formants, which entails that sibilants have relatively lower spectral energy frequency. This exposure will lower their threshold of identifying S on the spectrum continuum, and listeners will end up reporting more S. Similarly, participants in the lowered condition will hear lower vowel formants, which entails relatively higher sibilant spectrum frequency. And this exposure will increase listeners' threshold of identifying S on the continuum and make them report fewer S. So to summarize, the normalized distribution hypothesis would predict that the ranking of S report rate across conditions to be raised greater than normal, greater than lowered. Now let's jump into our results. The x-axis here represents 5 steps of spectral energy frequency from low to high, and the y-axis is the S response rate, and conditions are marked by color code. We can see that the 3 conditions differ from each other in the S response rate, with the ranking of raised greater than normal, greater than lowered, which is consistent with our normalized distribution hypothesis. Our logistic mixed effect model revealed a significant step effect and significant condition effect between the lowered and the raised conditions. So as an intermediate summary, we see that in the perceptual learning of sibilants, changing contextual vowel formants of a training speaker would affect listeners' sibilant categorization of a test speaker. This means that perceptual learning of spectral cues need to involve at least some degree of knowledge about speaker normalized distribution. And in the next, we'll ask whether this pattern holds for temporal cues, and we will address this question in experiment 2. So experiment 2 investigates TD, and we ask whether changing contextual temporal cues of a training speaker would affect listeners' categorization of TD in a test speaker's speech. Again, 45 participants were recruited to participate in the experiment online. So experiment 2 copies the setting of experiment 1, except that the target phonemes are changed to TD. It also contains 2 phases, a training phase with female A speech and a test phase with a female B speech. In the training phase, listeners will hear 17 words containing T, 17 words containing D, and 17 words of fillers. So the whole point is that listeners can get exposure to female A's TD and temporal cues in general. The test phase were designed to capture listeners' voice on set time categorization with minimal pairs such as tear versus deer. And the critical stimuli were constructed by splicing 5 steps of TD continuum into 7 lexical frames of TD minimal pairs. And again, all the trials were in each phase were randomized for each participant. So the participants are again randomly assigned to 3 experimental conditions with 15 participants on each condition. And the 3 conditions will have an identical test phase and identical TD on the training phase, in the training phase. However, the training stimuli will differ across conditions in the speech rate of the contextual speech materials. So compared to the normal condition, the contextual speech materials in the lengthened condition are temporally expanded by 1.7, whereas the contextual speech materials in the shortened condition are temporally compressed by 0.7. And the 2 hypotheses we laid out also make different predictions about our results here. So the raw distribution hypothesis would predict that listeners only learn and generalize the duration of the target phonemes. And since listeners had exposure to the same set of TD in the training phase, we should expect that they perform similarly across conditions in the test phase. By contrast, the normalized distribution hypothesis would predict that listeners keep track of voice onset time in relative to the duration of contextual speech. So in specific, in our case here, compared to the normal condition, participants in the lengthened condition will hear longer contextual speech, which entails shorter voice onset time of the consonant in relative to the contextual speech. And this exposure will lower participants' threshold of identifying T on the VOT continuum and make them report more T. Similarly, participants in the shortened condition will hear shorter contextual speech, which entails relatively longer voice onset time. And this exposure will increase listeners' threshold of identifying T, making them report fewer T. So to summarize, the normalized distribution hypothesis would predict the ranking of T response rate to be lengthened greater than normal, greater than shortened. Again, jumping to our results, the x-axis here presents the 5 steps of voice onset time from short to long, and the y-axis is the T response rate, and conditions are marked by color code. In general, the result followed the predicted ranking of T response according to the normalized distribution hypothesis, in that the lengthened condition has most T responses and the shortened condition has the fewest T responses. However, the supporting pattern was only found in the first 2 steps on the continuum. We think this might be because the whole continuum was quite T-biased, and the stimuli from step 3 to step 5 were relatively unambiguous, as you can see by the T response rate. So we can talk more about it in the Q&A session. Our logistic mixed effect model found a significant step effect and significant interaction between condition and step, but no condition effect alone. And this is consistent with our observation that the group difference here is mainly driven by the first 2 steps, which results in different categorization slopes across conditions. Okay, to start our discussion, we want to throw it out that studies on perceptual learning and studies on speech normalization were usually cited to support very different theoretical frameworks. So perceptual learning studies were usually interpreted to highlight the importance of phonetic details and the flexibility of linguistic representations, whereas normalization studies were usually interpreted to show that listeners are good at casting aside speech variability and arriving at abstract linguistic units. But our study provides some preliminary evidence of their interaction. We showed that listeners could learn and generalize speaker normalized distribution on the fly for both spectrum cues and temporal cues. The identification rates are ranked as predicted robustly across conditions in both experiments. Lastly, our findings shed light on the possibility to incorporate normalization mechanisms into current perceptual learning models using Bayesian inferences or neural network. That will be the direction of our future research. Thank you for your attention, and I'll take questions.